trying to find my okay, great. Okay, so I'd first like to thank the organizers for inviting me here, and I hope after my talk the rest of you might thank the organizers for inviting me here, but that remains to be seen. So I'd like to talk about a simple problem. Okay, it's basically how a crack progresses, and where's the pointer? Okay, the idea was to wake you all up at this hour of the morning. Basically, I'd like to take the simplest possible system that undergoes fracture, and I'd like to show you how it breaks. And the simplest possible system we can think of. I'm a physicist, so we can only do simple things, and we tend to make them complicated anyway, is to take a medium that is an amorphous brittle material. That's not me humming in the background, that's him. Okay. And to, I can just speak loudly. Let me just yell for these. Okay. Can I have the pointer, please? Okay, thank you. Okay, after that ado, I hope that woke you all up. So we can go into rock star mode now. I can wave my hands. I'm Israeli, that's what we do. Okay, so all of the stuff that I'll be telling you about is actually the work of other people. My graduate student, Itamar Korvin, and former graduate student, Tommy Goldman. And all I do is kind of watch them work and try to make sense out of it. So we're going to take a brittle and amorphous material, and which material it is, I'll tell you in a second. And we're just going to watch how it breaks. Simplest problem, no fancy boundary conditions, no fancy loading conditions, constant displacement, but we'll see that the way it actually breaks is a mess, and we'll try to make some sense out of that mess as we go on. Okay, fracture mechanics are what we need to know in half a minute or so. So, as we all know, crack develops as 1 over the square root of r singularity at its tip. That's why things break. Dynamic cracks have a speed limit, the Rayleigh wave speed slightly below the shear wave speed of material. Now, the dynamics of a crack are basically given, at least when they remain simple, by energy balance. So the energy release rate is equal to the fracture energy, or the energy dissipated at the tip of the crack. And we're going, for the rest of this talk, I'll talk about basically the framework of LEFM, linear elastic fracture mechanics, and I'll ignore what happens actually in the singular zone near the crack tip. If you're interested in that, this is an unpaid advertisement. I'm here and we can talk about it because we've done a bit of work on that stuff. Okay, first thing is, what material am I breaking? I'm breaking jello. Scientific jello at least, it's polyacrylamide gels. And I know half of you are going to turn off now. This is not steel, this is not, who cares about jello? But first, my first order of business is to convince you that you maybe should care about jello, because it's an excellent material for slowing down very complicated processes. And I'll show you the same characteristic phenomena that characterize the fracture of ordinary materials, such as the fracture of glass or maybe brittle acrylics. We see exactly the same things in gels. Why use gels? Because we slow down the Rayleigh wave speed by about 3 orders of magnitude. So we see the same processes occurring, but very slowly. And since it's slow, we can get in incredible detail about the structure of the fields around the crack tip and various other things that I'd like to tell you about. Okay. The first part of my talk, this is the experimental system that we'll be using. So basically we're applying constant displacement on just a rectangular slab of material. Now this is a gel whose samples are about 150 millimeters by 150 millimeters. And the first part of the talk will be very thin. It'll be about 200 microns thin. So this is really ostensibly kind of a two-dimensional material. We'll see in a minute that it's really not, but it's as two-dimensional as we can make it in the laboratory. As we break the thing, oops, I just turned this thing off, good. Okay, as we break the thing, we take a picture with a fast camera. The frame rate is around 10,000 frames a second or so. And each frame will give us the crack opening profile, as well as we've taken the face of these gels and put small grooves along them. So we've made a very tight grid of scratches on the face of this the crack. And this is a picture of a running crack. It's running at around half of the Rayleigh wave speed. And this is a zoom in. Here you can see the grid. So we have a 50 by 50 micron grid along the path of the crack, and we can use the deformation of that grid to actually back out the entire strain fields, the strain tensor at the tip of the crack, as it's running at dynamic velocity. This is one thing you can do when you break jello that you couldn't dream of doing something like this, breaking tool steel or glass or anything, just because it's relatively slow. Okay, so the first thing I have to do is convince you that this is not total bullshit, maybe partial bullshit, not total bullshit. So let's check the predictions of LEFM. So we'll look at the equation of motion for these conditions. So if we look at the equation of motion that's derived for an infinite medium under constant stress, basically this is energy balance. So we have the fracture energy equals the energy release rate, which is dependent for these conditions on the instantaneous length of the crack, the externally applied stress, and the instantaneous velocity of the crack tip. Now we can take this and derive the equation of motion looking at the instantaneous crack velocity as a function of the length of the crack. And when we do that, these are 4 or 5 different experiments that we've done, each one with a different applied stress. And we see that, okay, the dots are measurements, and the lines are basically the prediction of the LEFM equation of motion with absolutely no adjustable parameters. We've measured the fracture energy of this material separately, independently, and we've used that to show you the prediction, and it works extremely well. So if that was all that there was to say about dynamic fracture, then we could all go and drink coffee or hear actually an interesting talk that's coming up. But I promise you, we physicists take simple problems and complicate them. In this case, I don't have to complicate it as a physicist because nature will complicate it itself. This works extremely well because we've limited these data points to the moments where the cracks are simple parabolic crack tips and all that. But in general, a crack will lose its stability as it's propagating along. So now, the rest of this talk will be dedicated to understanding what happens when this simple crack that obeys this equation of motion loses its stability. But the point of this slide is just to show you that gels are perfectly representative of brittle materials. This is pure fracture mechanics. The only thing the gels did is slow down the Rayleigh wave speed in order to enable us to do these measurements, and the measurements that I'll tell you about in a second. Okay, so let's see what happens when cracks stop being simple cracks and start to become unstable. So when velocities become fast enough, and this is about a third of the limiting wave speed, a crack may lose its stability and generate frustrated microbranches. So we have a simple crack that will undergo frustrated branching events at some critical velocity. And here's a movie of what that looks like in jello. Okay, so as you can see, this crack is anything but simple. So here it's slowed down by about 1,000 times or something like that, but still, we saw a crack moving through gels at around 0.5, 0.6 of the Rayleigh wave speed. And what we find is that if we zoom in here at the fracture surface at which this crack is formed, we find that it's created these frustrated branches. So this is a picture of that, and that's a zoom in of that. So this is the main crack path is along here, and the crack spawns these tiny daughter cracks that can be microns in size. And okay, these are cracks that we see for this scientific jello, but basically they have the same structure as microcracks that we see in the fracture of glass or brittle acrylics. Okay, now I've told you that we can measure the strain field, so let's see what that means. So this is a map of the strain field, the YY component of the strain field, as a function of x is the propagation direction and y is the transverse direction. And these colored circles are not part of the strain field. That's just to show you that at various radii, we can take a look at, as a function of the angle, at the way that the strain field looks like. So each one of these colors is a different, this is the one that's farthest out, and the green one is the one that's closer. And okay, you can look at these and stare at them and say, okay, what am I supposed to do with this? Well, the first thing is that we can remember that we're talking about mode 1 fracture. Now, mode 1 fracture is symmetric along this axis. So the first thing you might say is that if you look closely, these peaks on either side of the axis of symmetry here, 0, are a little bit asymmetric. Now, you might say, these guys do bad experiments, but I may do bad experiments, my students do good experiments. So this is a real effect, this asymmetry. And you can barely notice it out here, but as you get closer and closer to the crack tip, it becomes more and more pronounced. And this cannot be part of this cannot be mode 1 fracture as we know it. So we're going to characterize this asymmetry by just its anti-symmetric part. So we're going to subtract each point from its opposite point and just look at the asymmetric part, throwing out 99% of the data. And let's try to understand where this asymmetry is coming from. And when we do that, we find that, okay, the closer we get to the crack tip, the more this asymmetry becomes pronounced. So this is the asymmetry that we just defined as a function of the distance from the crack tip. 0 is at the crack tip, so it kind of looks singular. And if we fit it to 1 over the square root of r, it actually seems to fit very well, and that's the radial part. But now, so the idea is that this is actually due to a very small mode 2 component that comes in, that exists during this experiment. So this asymmetric component is basically K2 times, this is the classic velocity-dependent K2 function, and it has a 1 over the square root of r singularity. And if we look at the angular part with no adjustable parameters except the value of K2, we see that it fits very well. So basically what's happening is that we have a small mode 2 component as this ostensibly mode 1 crack is propagating. Now we're going to use the value of K2 that we get from this to try to understand what the microbranching. So this is an experiment where a crack, as a function of time, is accelerating. And each one of these points is a snapshot where we've derived the strain field, the strain tensor. And what above is the value of the component of K2 that we've derived. And it looks like a mess. It's basically noise. Nothing jumps out at you or anything. And we're going to concentrate on 2 photographs. Okay. The green is the photograph right before we see a microbranching event. And the red is the photograph either during the microbranching event or immediately afterwards. So this is what the photographs of the experiments look like. These 2 little lobes that you can see here, that's where the microbranching event is taking place. So we're going to define this value here as a threshold value for K2. Now we'll say threshold for what? So let's take all of the threshold values that we see and plot them as a function of the instantaneous velocity at which this branching event took place. And this statistical mess actually comes down to a very well-defined line. So we have this threshold value of K2 as a function of the velocity at which the bifurcation took place. And we were kind of shocked when we saw that, because from such messy data, we wouldn't expect to see such a clean plot. So we see a systematic linear dependence, actually. And the higher the crack velocity, the smaller the threshold value of the mode 2 noise, if you'd like, needed to generate the instability. So basically, the material is kicking the crack as it's propagating along. Now, some kicks might do something and some kicks might not. Depending on how large the kick is, for example, a kick of this size at this velocity will do nothing. The straight crack phase, the straight crack is stable. If we kick it hard enough, though, it goes into a different phase, which we'll call for a minute the curved crack phase. And this line goes to 0 at about 9/10 of the shear wave speed, or very close to the Rayleigh wave speed. Well, what happens there, that means that any infinitesimal kick is enough to get this crack to go off axis. So what happens there experimentally? This is a movie of what happens at 0.9 of the shear wave speed, if I can get it to work. Okay. Here we go. So, this is in milliseconds here. This is our standard parabolic crack barreling along. It's accelerating, and then all of a sudden it starts to oscillate. It doesn't branch anymore. It's a wavy crack. Now the fracture surface of this wavy crack is entirely mirror-like. There aren't any subsurface features. Basically, at this point, the entire crack starts to curve out of plane. So, to summarize the first part of this talk, this is only the first part. You have to stay awake for the second part. Okay, what we've seen is we've discovered a phase diagram here that differentiates between a straight and boring crack to a curved crack phase, which corresponds to the microbranching phase that we talked about, the microbranching instability. We see that we've characterized the size of the kick necessary to cause a straight, simple crack to become unstable. And as this crack gets faster and faster, the size of this kick that needed to drive it unstable becomes smaller. And at a critical velocity here, at very high velocity, an infinitesimal kick will actually drive this to become oscillatory. Okay, if one looks at the fracture surface, one sees that when microbranching takes place in this phase, actually it doesn't take place homogeneously over the entire fracture surface. Our crack is propagating here from left to right. And this is now the Z direction, which I haven't talked about. But we can see that we actually have essentially bistability here. At the same velocities, we can have either a microbranching crack that these form in chains, or a simple crack over here. And these are kind of explained, and I won't get into it because I want to get into the next part, by this funny phase diagram. So we have what's called this is a transverse instability in terms of nonlinear physics, but we have a critical point here where straight crack at this point loses its stability, and it's hysteretic, and the size of the kick needed to go to this curving branch is basically described by this line here. So the picture that I'd like to show you is that microbranches are subcritical noise activated, spatially localized curved cracks. And so this threshold that we just saw actually explains the onset of the microbranching instability. And that's a happy event because somebody was born. Now we have to talk about, we're talking about life now, the life of these cracks. So now we're talking about the sad events when the thing dies. Okay, so we're going to shift gears a little bit. And we're going to move from a two-dimensional material to a three-dimensional material. So we're going to watch cracks as they propagate along a singular crack front, no longer a singular crack tip. So we're going to look at the three-dimensional behavior of the cracks, and we'll see that possesses the key for the depth of microcracks. Okay, so see, this is black. It's a sad event here. So we're talking about the death of these guys. So they're born by being kicked. You know, like the Bible says, we're born in pain or something like that. Don't personally know the exact quote. And I guess we die in pain too. So now, just to remind you, the fracture surface again has this bistability. So we have chains of microbranching events along given directions, but next to them we have simple cracks. So we'll talk about it. So this is obviously a three-dimensional effect, and we'll talk about that for the rest of my time. Okay, so different experiment now. How do we measure the dynamics of this singular front? First of all, we make the material thicker. So I'll be talking now about samples instead of 100 or 200 microns thick, they're 6 millimeters thick. And when we make it thick enough, if we shine light through it, we can look at the shadow of the crack front as it's progressing across the material. So we take a picture at 50 or 100,000 frames a second of a piece of this surface, and we see that the crack front becomes a moving shadow. And I'll show you some movies in a second. So this is a movie of a simple crack. This is from the side, so we're looking along the XY plane here. This is a boring crack, nothing really is going on. And this is what its front looks like. A boring crack front, nothing really is going on, but it's straight, as you can see. So we're looking again at the shadow of the crack front as it's moving across the sample. And the fracture surface, post-mortem, is basically as boring as the rest of this business. Nothing happens, it's a mirror surface. Okay, what happens now when branching takes place? So, this is our movie that we've actually already seen. So this is a movie of a branching crack. And this branching causes a number of parallel lines of these microbranches along the fracture surface. So again, our fracture is moving from left to right. And what we're going to do is focus in on one of these branches. Okay? So we're going to look at the crack front as it forms one of these lines of microbranches along the crack surface. And when we do, we find it's much less boring. We actually see this breathing structure. It looks cusp-like, and that's a hint of what to come, as it traverses the fracture surface. Okay, and this is a photograph of the fracture surface. This cusp is formed, and overlaid we have in yellow the instantaneous profiles of this breathing crack front. And you can see that this cusp-like breathing thing is actually what gives rise to the structure on the fracture surface. Can we make sense out of this? Okay, so now we're going to look at the life and times of microbranching events. So we're going to now zoom in on a single microbranching event. So this is a line, one chain of microbranches across the fracture surface. And we're zooming in on a piece of that, so that's this blurry thing here. And we're going to look at how the crack front progresses when it first meets this, when microbranches are excited, until the death of the microbranch, which should take place around here. So first we find that this is the instantaneous velocity at every point z along the width of the surface of the front. And this is the change in the stress intensity factor. It's derived, that we derived using the profile of the XY profile of the curve, and using this kernel that was derived by Rice and Gao a number of years ago. So this is a static kernel that gives us the relative change of the stress intensity factor at each point along the fracture surface. Now our equation of motion equates the change in velocity to the change in the stress intensity factor and the change in the fracture energy. Now every time we get a branching event, we're going to change the fracture energy. So when this branches, instead of a single crack, we have two cracks. So this contributes. Once a branch dies, then actually the only thing contributing to the velocity is this, basically this line tension given by the change in the stress intensity factor. Okay, so now we're going to step through. And right now, as you can see, the instantaneous velocity has become lower because we've started a microbranching event. So the fracture energy now is increased. Now, as we let this go through in time, it's becoming more and more stretched, so the stress intensity factor is growing as it's progressing, and the velocity is relatively low. Now, what happens when the branch dies? This guy will stop contributing. So we've taken a rubber band, we've stretched it, and for whatever reason, the microbranch decides to die, and now we're releasing the rubber band. So what's going to happen? Well, what's going to happen is that the velocity spikes. The instantaneous velocity at the time of the death of a microbranch, it jumps to, I don't know, 3 or 4 times its previous life. Okay, so the picture that you should have in mind is a slingshot. So the rubber band is caught by microbranch initiation and is released by microbranch death. Okay, so how much time do I have? 2 minutes. Okay, so I'm going to stop. I'm going to show you actually the death part. We're now going to bury these microbranches, and then you can ask whatever questions that remain unanswered. Okay, so the first thing is that I won't show you, okay, is that at the time of release, I will show you because it's fast, but the instantaneous change in velocity exactly is given by the instantaneous change in the stress stress intensity factor. Okay, so we understand what happens when we release the rubber band, but what about the death of the microbranches? So, for this we're going to use Mr. Burgers. So we're going to derive a Burgers equation here in 2 seconds. So, once a microbranch starts, or once actually a crack front meets any inclusion, it's going to curve the crack front. Now let's assume that the normal velocity is constant. Geometrically, if we take now the instantaneous slope of the front profile, and just under this assumption, we can actually derive a nonlinear equation for the propagation of the front. And this is a piece of a Burgers equation. Now, what do we know about the Burgers equation? We know that it actually derives an infinite curvature in a finite time. That's called a finite time singularity. So if we start with some initial curvature of the crack front, if we wait long enough, and the time that we have to wait is basically given by the initial curvature of the crack front and the normal velocity, a cusp will form in finite time. This is a catastrophe, if you like. Well, physicists call it a catastrophe. Some of us might call it the death of a microbranch, and I'll show you in a minute why. So, so this is an example of, okay, this T star is the lifetime of the time it takes to form a cusp on the fractures on the crack front. And we're going to compare this to the lifetime of a branching event. So what we're showing here, this is like a line of microbranches. And each time we have, this is the stretching of our rubber bands. This is delta, the relative change in the stress intensity factor. Rubber band stretches, dies, and each time, each one of these is characterized by some time, an hour or something, from the time that it's born until the time that it dies. And we'll compare the lifetime with the cusp formation time. To make a long story very short, okay, it works. So we have, this is the lifetime of a microbranch event, and this is the cusp generation time derived from its initial curvature. And okay, I've seen cleaner graphs, but it's a one-to-one correspondence with a slope of 1. So basically, the death of a microbranch happens because you derive a second singularity, a cusp-like singularity along the crack front. Nature doesn't like singularity, so when it gets sharp enough, it just kills the microbranch. So, I can just summarize now. I actually even did it in 30 minutes, 25 or whatever it was. I'm very proud of myself. I hope you're all proud of me too. But we've seen that microbranch birth is triggered by perturbations, but not just any perturbation, local shear perturbations. So there's a fluctuating K2 component. When it gets large enough, it generates the birth of a microbranch. And we've looked at how they die. So we see that they die because another singularity forms on top of the singular crack front, which is a cusp singularity. And once that forms, that's the mechanism that gives rise to the death of these things. And I thank you for your attention. Okay. And it's a line because that's the tip of the crack. But now, since this tip is extended along the width of the sample, it's the tip at every point. And it's contiguous. It's not, you could think if the material were kind of messy enough, you'd have a crack propagating here, here, and here. But it's not. It's a contiguous front. So this line is just the extension of a tip, a crack tip singularity along the width of the front. Okay, those lines, okay. Those lines are a microbranch triggering another microbranch triggering another microbranch. So it triggers actually when it dies, when one microbranch dies, as we saw, the instantaneous velocity becomes very large because we've released the slingshot. And then that's enough to trigger the next one. Kind of, not actually vibrations, because it's triggering out of, it's triggering a real microbranch. So you're creating another small branching event. But it dies because of this cusp that forms as a result. So actually the same process that gives rise to its birth gives rise to its death. I guess it's kind of like us in a on 1 foot.
This chapter.
Oh, does that work? Very interesting. Yes. Well, to what you said at the beginning, I'll thank the organisers for inviting you as well, because it was very nice to.
Well, cheap entertainment is always good. So.
I'm just wondering, do you not also get K3 perturbations, especially since you're dealing with thin sheets, and should you be wondering about that?
Good question. I don't know. I mean, because we're not sensitive to K3, but we're not missing anything in this picture. So maybe we're lucky enough in the way that we're applying stresses or whatever that we don't have to worry about it. We probably should, but K2 is enough at this time.
Okay, final question.
Range of strain rates. And the second one, if there's a kind of transition value of strain rate for this kind of area.
Okay, 2 simple questions. I wish I had simple answers. Okay, the first one I do, because these are, the strain rate is actually quasi-static. We're not, the way we do an experiment is we apply some constant displacement and then have a guillotine or something and send the crack along its way. So the strain rates are very slow, although the cracks are very dynamic. We can get nearly to the Rayleigh wave speed. 10 to the minus, yeah. The strains are relatively. I mean, the strains here are a few percent. They're large strains relative to standard materials. You know, we can get up to maybe 10% strain. So it's a lot of energy, but the rate is very slow. I would not be surprised if we had a knob that we could change the strain rates, that we would see different physics. But actually, this type of system is good for that, because things are so slow that you wouldn't have to worry. You could do very complicated experiments because you slowed down all the time scales by 3 orders of magnitude. But 2 very simple, very good questions, only one answer.